Hello, my name is Tseng from Boston College. I'm happy to share this keynote speech, how to make distributed system robust with the focus on high-performance state machine replication. The outline is that I will try to convince you state machine replication, or SMR in short, is very, very important and it's very difficult to achieve, and I will discuss some recent advances, and finally I will give you some takeaway and summary. Hopefully you will find this talk very useful. So I believe that all of you know that nowadays the modern internet infrastructure, we have this client server model. We as a user, we are client, we connect to the server, we make any requests, computation or storage, then bam, it's done. That's all good. But the thing is that when you have a very, very large scale cluster or service at the scale of Google or Facebook or even smaller scale, you are going to have some kind of failure. So one way to tolerate this kind of failure is to do replication or to do distributed service. So you have the same server, you have the same service, you try to replicate it. So even if like one of the server is done, you can still serve others. And then that's the key property of nowadays that modern infrastructure, modern system. We want to be able to scale. We add more machine, we can serve more clients, and we have a higher availability because there's redundancy, there's replication. However, one of the key challenge of this kind of replicated service is that you are going to have inconsistency. Maybe this set of client makes some requests, the other set of client makes some requests, and somehow one of the server fails, and then they don't have a consistency view of the world. They have like different data. In some of the application, it's fine, but in most cases, this kind of a scenario would make the development, would make the business, or would make the recovery very difficult to do. So one of the golden principle of a distributed system is that we want to have high performers, but at the same time, we need to do coordination between servers, between services. So the goal is that behave as if the whole service is provided by the single machine. So from the perspective of client, it doesn't matter which server, which like the cluster you are talking to. It's the same, exactly just one thing. And then that's what your expectation is. And one of the most common way of achieving this is to do state machine replication. In particular, it's called log-based state machine replication. So imagine that you have tons of clients, they are making requests concurrently. So this request can be anything. It could be computation request, or it could be that distributed storage. I'm going to read some data, write some data, do some transaction. Then the idea is that each server, you have a log. And then you have a discrete slot. So slot number 1, slot number 0, 1, 2, so on and so forth. And then client will make requests, and then the server will use some protocol that's called consensus to agree on the order of the request of the log. So suppose I request 2 somehow become the first thing that you agree on in slot 0. So request 1 being on 1. And the reason is that now we are distributed system. So there's a delay. Someone may not receive message in time. So there's a different view of the world. So for this replica, it hasn't seen the request 1 yet. But that's fine because we are using consensus. Everyone eventually will have the same log. And if you execute the request in the log sequentially, you are guaranteed to have the same view eventually. And then once you request it, you send a response back to the client, and that's good. Let's solve the inconsistency issue. even though the abstraction, the concept is very simple, there are lots of real world systems, real world applications. For example, Google, they have a log service, the file system, the data storage is also based on this kind of SMR, and Microsoft, OneDrive, Azure storage, and then lots of open source software. Cassandra uses consensus and machine replication to do transaction, Kubernetes to use consensus to do configuration, reconfiguration. It's everywhere, even though like you might not be aware of that, but like it's like kind of golden protocol to ensure robustness, to ensure reliability at the back end. Unfortunately, it is very challenging to do SMR with high performance and correctness and easiness of a development at the same time. And the reason is that if you recall the 3-step, one of the first steps is that you need to use consensus. And consensus is not easy, even if you are dealing with a simple case like crush failure. And in general, there are two categories of conditions or properties that you want to achieve. The first one is called liveness or termination, meaning that something good will eventually happen. So in the case of log-based SMR, eventually each slot you should have a request. And then for the safety, that you want them to agree on the same thing, the same order of request. So for each slot, you want agreement, the same request. And you also want to have validity, because this shouldn't be arbitrary thing. It should be some request proposed by a client. Very simple idea. But once you consider more realistic scenario, machine might crash, and then message may be delayed, they may be delivered out of ordering, everybody's in different set of message, then now becomes tricky. So in terms of model, we consider partially synchronous network, meaning that eventually the network will behave nicely, so all the message will be delivered roughly like the same. The replicas, they are going to see the same message. However, you will still have failure that might affect your protocol. And in general, we assume that they are n replicas and most have failures. And most important protocol to know in this domain is called Paxos. If you are from Greece, you from Europe, you might remember Paxos or recognize Paxos as an island, but it's actually not an island. It's a protocol that proposed by Leslie Lamport, who is a Turing Award winner. And then the reason it's called Paxos because Leslie likes to use metaphor, story, to convey his key idea. And then he described the protocol in a way that people try to agree on something on the island of Paxos, which is very interesting. And the backstory of this paper is also interesting. So I highly recommend you to check this website to see what happens when Leslie tried to publish this Paxos paper. But anyway, Paxos became so popular recently. There are tons of different Paxos algorithms. It becomes a family of algorithms, try to optimize, try to design for different things or like tolerate different kind of failure. However, even though like in terms of algorithm level, it's very elegant. But in terms of real world application implementation, it's difficult. So this is from the OSDI paper. When the author from Google, they try to implement this Paxos algorithm to support their service, their system, they found out that there are huge gap between the specification of the algorithm and then what they really need. And then in terms of like once you make certain optimization, practical implementation, the protocol becomes unproven because that once you throw in everything, it's a bit difficult to understand. And recently, actually not that recently, but like 8 years ago, a group from Stanford, they try to revisit this consensus protocol, and they say that, okay, people try to use consensus for SMR. Let's just build something for SMR and then have understandability in mind. And it quickly became so popular that most of the open source thing, when they try to adopt some consensus protocol, they went for Raft. So that's very good, but the story is not done. In terms of research, there are so many different things to think about. We have Byzantine failure, we have that wide area network, meaning that we are now not dealing with servers right now, we are dealing with data centers. And of course, that blockchain is also a form of state machine replication because everybody wants to see the same block in the same ordering or same set of transactions in the same ordering. It's solving consensus. And then there's also new techniques trying to improve something which is randomization. And now we also have a new kind of hardware that can speed things up. One of that is RDMA, remote direct memory access, which is very powerful abstraction that can speed up lots of things. And of course, the fundamental bottleneck of this kind of coordination is message delay. So once you have SDN, you have smart switches, you can push some of the work into hardware that can also make your life easier in terms of algorithm design. And in this talk, I will first talk about simplification. That's something that we as academia, we usually don't really appreciate until we need to implement it. When we discuss consensus or when we discuss SMR, actually the real world system is super difficult to implement because when we talk about consensus, it's only small ice on the sea level. But underneath the sea, there are tons of challenges that in the paper we don't even talk about, like how to do failover, how to do reconfiguration. When I want to do snapshot, checkpointing, how do I do that? And then when I have a log, you don't want to keep it to infinity, right? You need to do some compaction or garbage collection, and then it's not easy to do that. But even for Raft, it's still difficult. You need to take care of those auxiliary protocol, and because fundamentally both Paxos and both Paxos and Raft, they are leader-based consensus. So this just gives you some idea why that's the case. So in its simplest form, it's called multi-Paxos. So leader propose something, and everyone agree and then reply. So now you approve. That's fast path. You can agree on everything in one round trip. That's good, simple. What else? But the key challenge is that what happens if a leader fails? At this point, you already achieved something, some agreement, but no replica really knows whether the agreement has achieved or not. So when in the remaining time, replica 1, replica 2, they need to do recovery, try to do leader election or even re-election. And if during the process of the election, something fails, then it becomes tricky to ensure correctness. And typically when you do this election thing, it also is time consuming. And in fact, from the theory work, back in '83, there's already some protocol, it's called Ben-O's algorithm, that use the idea of randomization. So instead of multi-Paxos, is everything decided by leader, randomized consensus is kind of all-to-all communication. And the key idea is that they are going to make the joint decision. So in this case, leader kinds of make the decision, but in this case, everybody's need to exchange something and then output something. So we consider the same scenario, like replica 1 output something, leader output something, and then immediately after doing that, they crash. So recall that from the previous slide, we know that replica need to do election, which is expensive and it's difficult to do in real implementation. But in this case, for Ben-O, because replica 2 and 3, they get exactly the same set of message. They don't even need to have an auxiliary protocol to retrieve this kind of decision. And then that's one of the key benefits. But then once we observe this, we ask the question, why people didn't really implement or adopt this kind of band-nose idea? And the reason is that in practical sense, it's very expensive. You have all this communication, and then in its original form, it takes an exponential number of rounds to reach agreement. And then sometimes the performance is not very stable because essentially randomized rule is like flipping a coin, and then you want to have stable performance in practice. So in our paper published in SOSP last year is that we want to make this randomized consensus practical and fast. Is it possible? And the key observation is that right now the modern data center, modern infrastructure, actually the network is very stable. And then so that we can exploit this observation, this fact, to make randomized consensus work in practical. So what do we mean by stable? Is that roughly speaking, the majority of replica, they're going to see a similar set of message, and that's where we can hit the fast path to agree on everything in 3 message delays. And what do we mean by fast is that if all replicas, they propose the same request, then we are on his fast path. Everything can be agreed on 3 delays. And yes, it's not as good as multi-Paxos, everything can be agreed on 2 delays, but in real implementation, actually we can do better. And then that's our protocol called Rabia, Randomized Binary Agreement. And we use that as a key element to build SMR. And the key observation is that we have stable network and we can exploit it. And we simplify SMR because we don't need to do failover. We can do very simple log compaction and also reconfiguration. And more importantly, every proof is machine checked. So we are confident that it's correct. And then performance, it's even better than multi-Paxos and e-Paxos. And then for other case, that the network might not be that stable, but we are still comparable. So here's the evaluation. Again, we compare with e-Paxos. In this setup, e-Paxos is one of the fastest protocol, the highest throughput protocol that we can achieve. So we did it on Google Cloud platform, and then because it's in a single data center, the round trip is pretty good, and network is pretty stable. And then we can see that in the same zone, 99% higher latency. Right, our latency when we achieve the highest throughput is still very good, and then we are much faster in terms of throughput. Of course, when we consider the different availability zone, the network delay increases, the network is not as stable, but we are still comparable to e-Paxos. And remember, this e-Paxos is at 0% conflict, so it means that you can agree on any ordering. So, our protocol Rabia is that very high performers in this particular setup. Now we look at a different application of SMR, meaning a wide area network. So right now, it's a very common that we have one data center, maybe in Europe, the other in China, the other in America. So because we want to do geo-replication to make sure that we can serve people from everywhere. And even if some data center is down, unfortunately, we can still get our service back. But then in this case, leader-based design actually doesn't really work because for client, you try to read or write the data, the faraway server need to contact a leader, and then leader use consensus protocol to achieve the coordination and then getting back to the client. So here, this step is called commit. Basically, I want to determine the order of an operation or the order of a request. And as you can see, like all this round trip time is very time consuming for time sensitive applications. And for leaderless design is that anyone can try to make its own decision, then you save this one round trip, which is critical in the business world. And then one key idea for ePaxos is that we want this part to achieve optimal commit latency when we run the consensus protocol. And the way it's defined is confess path, meaning that this operation request can commit in one round trip. And then by commit, it means that after communicate, it only need to communicate with a simple majority. In this case, you only need to communicate with like one extra replica. And then when there's a conflict-free case, meaning that my operation and your operation, they don't conflict with each other, then we should be always on fast path. So ePaxos actually achieve both leaderless and optimal commit. So it's very good. But then last year, actually the group from Stanford find out that ePaxos is not as good as we thought, even though it's very good as a medium commit latency. However, when we compare the tail latency, which is very critical in most of the modern application, it's 4 times worse than multi-pixels because of its design. And then it's not very stable, so it really depends on application workload. And in the paper, they try to propose something to improve ePaxos. So this pink one is the original ePaxos, purple one is their improvement of ePaxos, and then this blue one is multi-pixels. And then you can see that yes, after improvement, median latency improved, but I consider tail latency is 99 percentile right now. Multi-pixels is still much better. What happens? The reason is that ePaxos try to achieve the optimal commit, but they sacrifice this property called instant execution, meaning that I commit, but it doesn't mean that I can execute the execution when I see, even if I already agree on the order. And ePaxos, because that the way they do dependency tracking, they are not able to, it's not able to achieve this. And then also last year, the paper called Tempo, published in Eurosys, is very good. They propose a new way of to decide when it's possible to commit a request, and it turns out that it's much faster than ePaxos dependency tracking. And then the key contribution is called timestamp stability. And then they test it on AWS. And then as you can see that the tempo is far out here. And then all this thing like flexible Paxos is kind of like multi-Paxos in terms of performance. Caesar is something better than multi-Paxos. And then as you can see that tempo is the fastest among those because of their normal usage of logical timestamp. However, in terms of tail latency, is still not the greatest because there's no instant execution. So the question to ask is that, can we achieve that? And then it's actually possible. It's our protocol called GUS. And then for this, we don't really focus on SMR anymore. Instead, we focus on both SMR with the application of distributed storage in mind. And then that's the way that we can achieve this. And then in terms of evaluation, we, due to the interest of time, let me just show you one thing. Like GUS, ePaxos, as you can see, is like pretty slow in terms of tail latency, but like for us, the orange one, we can achieve a one round trip right in this case, and in most cases. And then for the read, we can always achieve one round trip read, and then the best protocol out there is called Grid, and then we have a better performance because our design exploit a better way of agreeing on the ordering of operations. So the summary is that SMR in practical system is super difficult because all of the things I talk about, it's hard to tolerate failure, it's hard to implement it, it's hard to understand. And then, yes, we have tons of leaderless protocol right now, but like to my knowledge, in real world, people are still hesitant to adopt those because it's complicated. And then in terms of research, there are still many open problems. How do I reduce engineering complexity? How do I make use of new hardware? How do I do blockchain? When we have Byzantine, when we have permissionless, it becomes even more complicated. So where to go from here if you are a practitioner or if you are building some reliable distributed system, but you don't really work in this area? Here are two advice. Be very cautious on the system that you are going to use, the protocol you are going to adopt, because it's tricky, it's complicated stuff. And then you want to make your decision very wisely. Here are two kind of survey paper or study paper to tell you that when you are going to adopt something, SMR or consensus, how to make the decision. That's all I want to share. Thank you. If you have any questions, feel free to email me or I will be happy to answer in any form. Thank you.